So do you have any, going back, do you have any questions regarding? Oh, yes.
How do you explain the increase in pressure and volume?
So the question is about the van der Waals gas, and how do you explain what?
Yes, okay, according to the formula, the increase in pressure and increase in volume.
Look at this. So actually, one of your friends has sent me a PDF of the contour plots done with Mathematica, and I strongly suggest that you guys this is 1 mole of van der Waals gas. Okay, so your friend wants to know why you have for T less than Tc, you have something like this. It's just the equation, okay? Just the solution of the equation. For when you solve for P as a function of V, you plot it for, there is a critical temperature below which the curve has this shape. Okay. So as we said last time, or maybe the lecture before that, I don't remember, this curve is not physical in the sense that it's not what you find in a lab. What you find in the lab is that you go up from the gas, and then at a certain point you start generating liquid, and until all the gas is transformed into liquid, the pressure remains constant. And then when you have all liquid, then the pressure starts increasing again. Based on the on the second law, that says that that implies that for a isothermal cycle, the work done and heat exchange are 0. We established Maxwell's construction, which tells us where we have to put this straight line here. And the straight line has to be put in such a way that the area under the curve here and the area above this curve here are equal. Okay, so just to refresh your memory, we did this construction by considering a cycle in which all liquid, you start with all liquid, then you go up to this curve, and then you go down here. You have all gas, and then you follow this thing here. This cycle is reversible, and therefore we can apply the theorem that I just mentioned before. And you find that the work done has to be 0, so this area has to be equal to this area. We also explained why we cannot apply this theorem to separate it to, let's say, this cycle here. And do you remember what was the explanation? Not? In which the transformation is not? It's not reversible. There is a point at which the transformation is not reversible, because there has to be condensation of gas into liquid. All right. So my answer to your question is either with the computer or with pen and paper, or with a calculator, with one of those graphical calculators. Take this equation, solve it for P, write P equal blah, 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 put T as a constant, less than Tc, you have to find the value of Tc. It's a function of A and B. And plot it as a function of V, and you will see that it has this shape here. Okay? the question is, what is the order of the constants, the order of magnitude? And that depends on the gas that you're considering, but they're not too big. Usually well, okay, they are something. We can go in the books and find the values of A and B for 1 mole of, I don't know, what, CO2 or something. But on the top of my mind, I don't have the actual numerical values of these constants. Also because it's not the constants which are important, but it's the critical temperature. The critical pressure and the critical volume. Or the critical density if you want, because we are talking about 1 mole, so the inverse of of Vc will be a critical density. Okay. So this is to stress that there is I can explain things to you up only to a certain point, and then you really need to sit down with a piece of paper and plot graphs. Okay, probably in all of the exercises of the problems that we'll do for the test, there will be plotting of functions. Okay, so we have a certain function. These are the parameters. Show either a qualitative plot or a quantitative plot. Okay, so if you don't know how to plot a function, what's the difference, for example, between the function 1 over x and the function logarithm of x? Okay, you cannot pass the exam. Okay, this is very important. You cannot do physics in general if you don't know that, but in particular, in this situation, you cannot pass the exam. Okay, so today I want to introduce thermodynamic potentials. We will go back to this equation many times, so please do some exercise in your spare time and practice and try to understand the peculiarities of this equation, because we will use it as a test case for many properties. As we use the ideal gas equation for many properties to calculate work and other things, but there are the existence of a critical temperature and of a critical point here in the van der Waals gas is peculiar to the van der Waals equation. We cannot use the ideal gas equation. That's too rough an approximation. Okay. So let me remind you that if we have a transformation between between A and B, the entropy difference, which is equal to the integral of dq over T on a reversible cycle, it's always larger or equal to the integral on an irreversible cycle. A reversible transformation. Sorry, it's not a cycle. It's a transformation from A to B. Okay, so for an isolated system, which does not exchange any heat with the source, with the environment, this thing is equal to 0, okay? And the change in entropy is always positive. Okay? So for example, if we have a gas, ideal gas, which is confined in a volume VA, and at a certain point we let it out, we pin a hole in the little box VA, and we let it go out to occupy the volume VB. The increase in the entropy is positive or negative? The change in entropy is positive or negative for this process? It's positive. Okay? We can actually test this thing. We can actually test because we know the expression of the entropy. The entropy is a function of temperature and the volume. And it's CV log T plus for 1 mole is just 1 times R logarithm of V plus a constant. Okay? So since VB is larger than VA, so this is an ideal gas. Right? So we let it expand. It does not do any work. So if it has a temperature T to begin with, after it expanded, it has a temperature. Temperature decreases. Why? -3. 3 more to go. Why does the temperature go down? The volume, you say the volume increases and?
The proportion is inverse.
Why? The equation of state? Okay, but first of all, this process is reversible or irreversible? -2. So the equation of state is satisfied or not satisfied during the process? It's not satisfied, so we cannot follow it. And the second thing is the pressure. Is it a constant or not? In principle, it's not a constant, right? So the equation of state links pressure, volume, and temperature. But if we don't know anything about the pressure, we cannot infer. Okay. We cannot infer anything. Okay. The temperature does not change. We said it many times. For an ideal gas, if the gas does not receive any heat from the environment and does not do any work, the temperature does not change. Why? What does the first principle say? The change in internal energy is equal to Q W. Okay. So this is 0, and this is 0, so this is 0. So what does this have to say about the temperature?
The internal energy is a function only of the temperature.
For an ideal gas. Okay? So if this does not change and it is a function only of the temperature, in particular for an ideal gas, it's an explicit function of the temperature. It's a function that we know. It's CV times T plus a constant. So if U does not change, then T does not change. Okay? So delta S is CV log of T divided by T, which is 1, log of 1 is 0, R log of VB divided by VA. But since this is larger than 1, then this is larger than 0. All ds is larger than 0. Okay? So the second principle tells you that spontaneous transformation that do not require work acting on the system or giving heat to the system. So in an isolated system that does not perform any work, the entropy just increases. In fact, as I said, this is supported by tons of experimental evidence, and also by the fact that nobody has ever observed gas contained in one room just spontaneously go and sit into a smaller volume. Okay, we always witness the opposite. All right. So for an isolated system, which does not perform any work, does not exchange any heat with the environment, just completely isolated, the system goes to a state of maximum entropy. Okay? If the system can perform a transformation that raises the entropy, it does it. Okay, so let's keep this in mind. This is just I'm just repeating what I said in the second lecture. So we are now going to talk about thermodynamic potentials, as I say. So what's a potential? What's an example of potential that you know? Electric potential, okay? Or anything? Gravitational potential. Okay? What do potential have in common? What's the definition of a potential? For example, gravitational potential. What's the definition? The gradient of the potential is a force. Very good. That's the definition of potential. But from this definition, or an equivalent definition, is that changes in the potential is the amount of work that the system does. Right? Okay? If I have a mass here, and I don't know, there are some pulleys and other things, and this is attached to an engine or something. If the mass drops of a mass of 1 kilogram, if it drops of 1 meter, its potential energy changes, and the change in potential energy is equal to the work done by the system, okay, which in this case will be minus m, which is 1 kilogram, times g, which is the gravitational constant, times delta h. Okay, delta h will be negative, and the potential will increase. And so we get the work done by the system. Actually, sorry. Okay, so we have some work done by our system. So as we saw in thermodynamical system, there are other ways of storing energies which are not ordered as in this case, in which and there is just one coordinate. We can bring it up, down. We can do whatever we want. So for a thermodynamic system, we know that the work done is minus delta U plus Q, okay, which is the heat given to the system. Suppose now we consider a system which is not isolated, but rather it's in contact with an external source at constant temperature. Okay? The system is at equilibrium with the source. At the beginning, it has a given temperature T. So we use this fact, and we get that the heat exchanged in a transformation between A and B, since T is constant, we can bring it out from the integral, and this becomes delta Q, or Q, actually. And from this inequality, this is less or equal than SB minus SA. The equality sign is only true if the process is reversible, which means that it goes through a series of equilibrium states. The increments are infinitesimal, and at every point, the equation of state is satisfied. Okay, so the work done is minus UB minus UA plus Q, but Q is less or equal than TSB minus SA. Okay. So let me define this function, which is U plus minus TS, sorry. And which is called the free energy, or Gibbs free energy, from the name of and if we define this function, then this is, sorry, this is less or equal than, because I've used this equation now. Okay, so I have again an inequality, and the equality is satisfied if the process is reversible. And you see that the work done by our system is less or equal than minus the change in the free energy. So this free energy behaves like, in this situation, this particular situation, in which we have a transformation which occurs by, with contact with the source at constant temperature. So you could require that the system is also itself at constant temperature throughout the transformation, but this is not necessary. The important thing is that the exchange, the external source, which is very big, is at constant temperature, so the heat exchange is always at a given temperature, at the temperature of the source. And therefore, let me write this down. Well, because it's free in the sense that it's the energy which is available to be extracted by the system. Okay, it's not like the potential energy. It's like the potential energy in a non-thermodynamic system, in a simple Newtonian mechanics, very simple system like this. And the change in this function is it gives the work done, gives an upper bound to the work done by the system. Okay. In order to have equalities in thermodynamics, you always have to require that the transformation is reversible, because otherwise you can have irreversible processes that waste some resources like energy. Okay, energy goes in a form that cannot be reobtained. Okay. Yeah, there are two questions. The question is whether this energy exists always. Okay, the question is whether the free energy always exists. And the answer is, as a function, yes, because it's just the internal energy minus temperature times the entropy. Since the internal energy is always well-defined, and the entropy is always well-defined, and the temperature is always well-defined, I can define this function here. Uh-huh.
Yeah, it means that energy exists is not due to transformation or hence you have a system this energy.
So the question is whether this energy is a property of the system and always exists. And the answer is yes. It describes the internal state of the system. Okay. Like the internal energy and the entropy, they say something about the internal state, the thermodynamic state of our system. And moreover, it has the property, the peculiar defining property, that in a transformation that occurs at constant temperature, so in contact with an external source, it gives an upper bound to the work done by the system. Okay? So it exists. It describes properties. It contains information about the internal structure, whether there are molecules, they are atoms, whether they are, I don't know what, you name it. Whether it's in crystal form, whether it's a gas or a liquid. The free energy knows this thing, quote unquote, knows these properties, and returns a numerical value when you compute the difference between 2 points. That tells you, in this transformation, for example, if delta F is minus 10 joules, then you can say, in this transformation, I cannot get out more than 10 joules of work. If I do it reversibly, so slowly, going from equilibrium state to equilibrium state, then I can get out exactly 10 joules. This is the information. So it's very generic in the sense that I don't have to describe the microscopic workings of the system. And it's very powerful because it gives this information, which is very useful for understanding what. Okay, you had another question. It was on the same line. Okay.
Do we have a system with? Do we have a lower bound for the free energy?
Not for the free energy itself, because it's defined like the internal energy, and the entropy is defined except for a constant. So you cannot have a lower bound on the free energy, but clearly you can only talk about differences in free energy. Okay? Whenever you want to know something about the overall constants, microscopic properties of the system have to come into account. I showed this to you when we talked about the third principle of thermodynamics, which says something about the overall constant says also something about the overall constant in the entropy. but this is true also for the overall constant in the internal energy, and they both come into play with the free energy. Now, following the same reason that told us that for an isolated system that performs no work, the entropy had to increase in any transformation, in particular in irreversible transformations, otherwise the equality sign is conserved. If we have a system which is in thermal contact with the environment at constant temperature, but does not perform any work, then this is equal to 0. And we have that dF is less or equal than 0. So this means that sorry. In spontaneous transformation, irreversible between that go from A to B at constant temperature, the free energy has to decrease. Okay? So you can have, in a thermodynamic system, you can have an increase in internal energy, spontaneous increase in internal energy, if it is compensated by a sufficient increase of the entropy. Okay? Because these two terms have an opposite sign. So at 0, so this, okay? So this is important. For a system which is not isolated, but it's at constant temperature, so exchanges heat with the environment, the correct statement is not that the entropy increases, but that the free energy decreases. Okay? And in fact, this contains some, suppose we consider 0 temperature, then this term here drops out. Okay, and we are left with the free energy which is equal to the internal energy at 0 temperature. And as you know, when systems are ordered, they always try to go to points of lower energy. Okay, so this principle reduces to that we already know in Newtonian mechanics. The systems try to go for the minimum of energy. When the temperature is very large and the internal energy is negligible, then our system will always try to go to points of higher entropy. Okay? Because when the temperature is very large, motion is very chaotic. And very chaotic motion likes to explore regions of higher entropy, which is understandable in terms of the connection that we made between the entropy and the probability of a macroscopic state. The number of microscopic states which are compatible with the given macroscopic state. Okay? All right. The question is, can we calculate? You always have questions about universe, galaxies. The question is whether we can calculate the entropy of the universe.
So, how can we get the heat?
Look, the universe I mean, this is a profound question. I don't think it's a stupid question. I think it's a very profound question. The issue is with the tools that we have now, we cannot answer this question. Okay? We can talk about. We are happy to talk about smaller things that we control. If you start talking about the universe, you have to talk about a whole lot of things. Quantum mechanics, gravity is not negligible on interstellar distances, and all these things. So people have tried to answer these sorts of questions. If you read Stephen Hawking's books, there are a lot of these things. Okay? The state of the universe, the wave function of the universe, the entropy of the universe, these sort of things. Okay? So there is debate in that. But with these tools that we have here, we cannot hope to answer that kind of question. Okay.
So we can say that for the universe, the computation of entropy doesn't follow the same thermodynamics.
No, it's not that the computation of the entropy for the whole universe does not follow these rules. It's that the very concept of entropy for the universe has to be treated quite carefully, right? Because one could always argue that there is one state of the universe. Why many states? It's not. So one has to be careful. I don't want to enter into this discussion because it's very slippery. Okay, I might say something which is not true or was considered to be true 10 years ago is not true now. So.
Can we roughly estimate if we take our sun as a thermodynamic system and then the free energy?
If we take what, sir?
Our sun
Uh-huh.
as a thermodynamic system, and then how much more can we extract? I mean, the free energy.
As I say, you can only measure differences of free energies.
Okay, train the difference of the free energy.
Well, people have studied thermonuclear reactions in the sun. These are well studied, and people know what's the work that you can extract. You have to do this sort of calculation. You have to calculate both the increment, decrement in internal energy, taking into account all possible sources, nuclear, chemical, and everything. Okay, changes of states and so on and so forth, and also the entropy. Okay, so it's a general rule in physics, just to go back for last time on this sort of question. When Galileo started putting down the rules to follow, okay, and when Newton and Galileo started talking about the rules to follow to do physics, okay, one of the rules was that the phenomena that the laws that describe the things that happen on the Earth are the same of the laws that describe things that happen on a distant planet, in the stars. So the universal laws that we discovered by analyzing steam engines, they are valid for the sun, they are valid for galaxies, they are valid for the entire universe as a whole. It's not that the laws that I'm describing are not valid. They are. They are true for the experiments we do on the sun. They are true for thermonuclear reaction on Alpha Centauri. They are valid everywhere. It's just that the situation becomes more complicated if you ask a complicated question. So it's better to understand small things first and then try to go up and understand big things. Okay? Okay. So as an application of free energy, let's consider isochord transformation. And how the work done changes when we change the temperature. Okay, so let's consider this transformation. This transformation is isothermal, and this construction is called Van 't isochord. Van 't. The transformation is not, and this is an isothermal transformation, not an isochord transformation. What's an isochord transformation? Constant volume, right? Okay. So the constant volume enters now. When we say, okay, let's consider the work done in the transformation from A to B. It's minus f of v minus f of a. Let me call it minus delta f. The equality sign is because the transformation is reversible. You're becoming quite fast in answering reversible. Yeah. So let's consider now two other points, A prime and B prime, okay, which are at a temperature T infinitesimally larger or smaller, depending on whatever you want delta T to be larger or smaller, to A and B, but at the same volume. So here is where the isochord enters, okay, because this volume is the same. Okay, so L A prime B prime is equal to minus f of B prime minus f of A prime. And we want to look at the infinitesimal change. Yeah?
Should we use W or L?
Oh, right, you're right. Sorry. You know what? Okay, so the book uses L. Okay, but it's the only book written in English which uses L. And you know why? Because Fermi used L at the blackboard. He arrived in the States in 1934. These lectures are 1936. And L work in Italian is lavoro. Okay? So he was using L because it's the letter for work in Italian. And the student that wrote down the lecture notes kept using L instead of putting W. So I'm switching between W and L. So, okay. Yeah, in fact, here I have L all the way. Anyway, so if the increase in temperature is infinitesimally small, then WA prime B prime will be equal to WAB plus a small change, right? And by taking the differences, we say that dW is equal to dW by dt is equal to minus dF B by dt at constant volume plus dF by dt at constant volume. But dF is equal to du minus TdS. Sorry, let's do this. So ds is d of u minus ts. So it's du minus tds minus s dt. Differentials have exactly the same properties as derivatives. When I take the differential of a product, is the sum of the differential of one term times the other, plus the one in which we exchange the two terms. Okay, so here I'm looking at the change in free energy between B and B prime. So that's why constant volume, because I defined B prime as being the point B with the same volume and just slightly higher temperature. And therefore, du is equal if there is no volume change, there is no work. If there is no work, then du is equal to dq. Very good. Which is TdS. Okay, so this term and this term just drop out. And dF is equal to minus S dt. Okay, so dF by dt is equal to minus S. But S is F minus U divided by T. Actually, minus S is F minus U divided by T. So
Which line?
what?
Which line?
Both. For both. They are both isochord transformation. So both for dF of A by dt, we get F minus U divided by T. And for dF of B by dt, we get the same thing. So, T dW by dt is equal to minus F of B minus U of B plus F of A minus U of A, which is, let me write it like this, L plus du. Okay? W plus du. And therefore, we get this equation. So the work done on a transformation satisfies that differential equation, which links it to the energy change between the initial and final point of the transformation. This is true for any transformation. Okay, so for example, let's make an example. let's take the ideal gas. So let me erase the derivation, and let's just keep this thing. Okay, so on a isothermal transformation, the change in internal energy is 0, right? So for the ideal gas, W between A and B satisfies W minus T dW by dt is equal to 0. Okay? What's the solution of this equation? W is equal to proportional to T. W is proportional to T. Let's write the proportionality constant alpha. W is alpha T. Is this correct or not? For the ideal gas. For the ideal gas, we can do the calculation exactly. Okay? We have an isothermal transformation between A and B. What's the work done by this isothermal transformation? What? Yes. Yeah, but what's the proportionality constant? CV? No, it's not equal. Okay. It's, well, who wants to try? It's equal to Q, but I want an explicit expression in terms of the VA and VB and T. R log of VB over VA, and there is also T. Okay. So from this isochord transformation, and as an application of the free energy, we see that we can immediately say that W has to be proportional to T. But the proportionality constant, we cannot get it, because we are doing transformation at constant volume. So this constant depends on the volume. But the important thing that we can say is that for an ideal gas, without doing any calculation, integral P dV, blah, blah, we don't know anything, we can say that the work is proportional to the temperature. Okay? What about van der Waals gas? Along an isotherm, du is equal to 0 or not? It's not only a function of t, right? So du, u is a function of t and v, and it's a function on, let's say, one function of t, which does not depend on the volume, and we say based on van der Waals gas equation of state, we cannot determine what this constant is. But there is a term. Let me get the sign correct. Okay. There is A, which is the same constant that occurs in the equation of state, divided by V. So du on an isothermal transformation is 0 because this thing does not depend on the volume, depends only on the temperature, and the temperature is constant. But then we have minus A, 1 divided by VB, minus 1 divided by VA. So it's not 0. So in this equation, we have not 0, but we have minus A okay? Now, what's the solution of this equation now?
Okay, in general, we can read, okay, we will have the long term and then 1 over VA. I mean, in principle, we have to reduce the solution of this thing when we set A is equal 0 to the ideal one. So we have to see something like that looks like the ideal one. So I suppose there will be line, okay, T 1 over VA minus A something. But in principle, we can solve it. I mean, the homogeneous one plus the quantity.
Okay, that's correct. This one is particularly simple, though, because this constant here does not depend on the temperature. So the solution is particularly simple. Is something proportional to the temperature, a constant that we cannot, minus A 1 over VA VB. Okay. This depends on the volume, but not on the temperature, this constant. And this depends on the volume, but not on the temperature. And in fact, if you integrate PdV to get between VA and VB, dV P is equal to RT divided by V minus B, and then we have plus A divided by V squared. So we get RT log of VB minus B divided by VA minus B, and then we have minus A 1 divided by VA. So now the constant alpha okay? Very good. So this was just an application of the free energy. Let's look at so I'm showing you examples of how these things work for ideal gas and for van der Waals. Because I want to show you that these things are not specific to any system. These equations, these inequalities or relations that we find between thermodynamic variables have to be satisfied by all systems. Okay, when they are not satisfied by some system, it means that something is wrong. But so far, they are widely used and they work very well. Okay, let's consider an isothermal infinitesimal transformation. The work is PdV, as always. The change in the free energy is isothermal. So thermal transformation. The change in the free energy is only due to the change in volume. Okay, so as the work done is equal to minus du, minus dF, okay, isothermal, we said. Then we have that PdV to be equal to minus dF dV, constant temperature times dV. So pressure is the derivative of the free energy with respect to the volume at constant temperature. Okay, so for example, again, for an ideal gas, by using U minus Ts as an expression, we find that it is Cv times T minus T, Cv T plus R log V plus constant plus another constant U0, which is. And again, if you take minus dF by dV constant temperature, you find dR over V, and we say that this is the pressure, and so we recover the equation of state of an ideal gas. So let me show you actually this. So if F is U minus Ts, dF is du minus T ds minus S dt. Du is for a gas or for a system which has a PV phase diagram is P dV minus TDS plus TDS minus PdV minus TDS minus SDT. So you see, if I only look at the internal energy, it's like the independent variables, the x and y, are volume and entropy. Okay. So I'd say the natural variables in which to express changes of internal energy are volume and entropy. So, but if I now add this Ts and I take the differential, you see that now this goes away, and now the natural variables in which to express changes of this new function, which is a free energy, are volume and temperature, which are more natural, if you want. So this is an example of something which is called Legendre Transform. But the only thing that you need to know is that dF is minus P dV minus SDT. So if a transformation is done at constant volume and constant temperature, then dF is equal to 0. While this is not true for du, because du is minus PdV plus TdS. So if the temperature is constant but ds is non-zero, then the internal energy changes. So we could do the same game, but now consider systems which are at constant. Is this clear? I mean, this calculation is very simple. It's just the cancellation which is enlightening and shows that we're actually going from SV plane to a TV plane. So constant temperature and pressure. It's getting more and more difficult. We keep more and more things constant. So we say that the work done is limited by minus the change in the free energy. But for constant pressure, the work done is P dV. These are now not infinitesimal differential. These are finite differences. If the pressure is constant, I can write this as the difference of PV and with the same trick, if I define the function phi as f plus PV, then d phi is less or equal than 0. Okay. So this thermodynamic potential has to decrease for transformations that occur not at constant volume, like free energy, because we said if the system does not do any work, so constant volume, and it's a constant energy, then the free energy has to decrease. If we do not impose that the volume is constant, but rather that the pressure is constant, which is natural in many settings. For example, when we talk about solids or liquids, it's very difficult to keep the volume constant because the compressibility of a solid is very small. So you have to apply a large force. So it's better to talk about constant pressure. This thermodynamic potential has to decrease in transformations which are irreversible or is equal to 0 if the transformation is reversible. This is sometimes called also enthalpy for reasons that I will have to look at. So d phi is then equal to dF plus P dV plus V dP. Okay. But dF was equal to minus P dV plus S dt. So you see that d phi is proportional to a differential of t and a differential of p, showing that the natural variables in which phi is defined are t and p. And in fact, when t does not change and p does not change, phi does not change. Okay? So, from this we see that the phi in dP at constant temperature is equal to the volume, and the phi by dt at constant pressure is equal to the entropy. If you look at the expression of f, f is minus df is minus p dv plus s dt. What? Minus s dt, you sure? Mm-hmm. Oh, right, you're right. Minus, minus. Okay, so we had that df in dv at constant t is equal to minus p, and df dt at constant v is equal to s. Okay. So as an exercise for you, you know the expression of internal energy, you know the expression of the entropy, just for an ideal gas or for a van der Waals gas. Try to calculate, try to use these thermodynamic relations and try to see if it works. Okay? So you know that phi is f plus pv, f is u minus ts, so phi is u minus ts plus pv. So you know the expression of this, you know the expression of this, put the pressure from the equation of state, put it in, you have a very big expression, take derivatives, and see if these equations are satisfied. Okay? In this way you learn a little bit how to do these computations, and you do some exercise, which is always good. Okay, now I should start talking about different phases, but and the equilibrium between phases. But I will do it. I will do it tomorrow. Okay. Yes. Yes. Yes, thank you. Okay, so let me stop here.